So what I did is I kind of looked at the things that we studied in this unit, and I tried to make like just it's just short PowerPoints, like 12 slides, just kind of going over like the major points of this unit. Sometimes I like when we get into like velocity and acceleration, I can do like specific questions that are really similar to the test questions, but there's about a million different ways that you could ask like a Sig Fig problem or something like that. So it wasn't super practical for this unit. Um, so the first thing that you guys, I think, learned was this conversion stuff. And I found this graphic online and I thought it seemed really good because sometimes they say, like decimals and stuff. And I think that makes it difficult when you're trying to like do your conversions because then sometimes students will put decimals in their little train track thing, which I'll show you on the next slide, instead of like the actual whole numbers that they needed. So basically, if you're going to the bigger side, which is the side on the left, let me see if I can get this to work. Okay, if you're going to like anything on this side, um, you're going to divide by numbers. So like whatever you have is going to get smaller if you're going this way. Your answer will look smaller. And then if you're going to something that is small, which are these three on this side, then you'll multiply and then your answer will look like it's bigger, if that makes sense. There is the same amount, it just looks bigger. So let's see. Okay, so here's an example question just to kind of give you an idea. Okay. So basically I'm going to put what I know first. So that's that 158 kilometers. Okay, and then I need to do, like, there's this thing that they call like a train track. Let me see if I can get it to work again because, um, here we go. Okay, excellent. It doesn't want to use my pen, but it'll use my mouse, so that works. So I draw this kind of little thing um, just because it kind of keeps me organized. And then I put, since I have kilometers up here, I'm going to put kilometers down here. And then I'm going to put what I want up here. Okay, and now I don't like to go straight from kilometers to centimeters. A lot of people do. They can, and that's fine. I actually like to kind of go from kilometers to meters, and then do like one more step and do meters to centimeters. It's one extra step, but I feel like you're a lot less likely to make mistakes this way. And so this is the way I kind of like to do it. So, I mean, you can do it the other way. It's totally fine. I just, I see a lot more mistakes when people try and go straight from kilometers to centimeters because they're going from a big thing through that middle unit, which is meters, all the way to centimeters, which is small. So that way then these will like cross out and then your meters will cross out and then you'll be left with centimeters. So here, I'm going to say how many meters are in a kilometer. Okay, and it's 1,000. I usually make my students in the face-to-face classroom memorize this, but honestly, you could probably have it written down for your test, and you would be fine. But as you work through the course, you'll probably accidentally memorize how many meters are in a kilometer anyway. And then because centimeters are small, I like to say how many centimeters are in 1 meter, and that prefix centi means 100. So there's 100 centimeters in 1 meter. So then I'm just going to do 158 times 1,000 times 100. And so then I'm just gonna take those zeros and plop them in my number. And then once I have the zeros in, then I'll kind of write my commas. So I have my 3 zeros from 1,000 and my 2 zeros from 100. So then I'll go comma. So that would be my answer. Now, if it's a quiz question and it's a multiple choice, they're going to already have these units here for you. But if it's not, if it's a short answer question where they give you like a little text box, you're going to need to show your work. So you'll have to like kind of show your work somehow. A lot of folks like to write it like this when they show their work in the text box. They'll do something like this, 1,000. Yeah, I wish my pen would work. They'll do something like that. So they'll just kind of put it in fractions. No, it's actually like a little text box, and so you have to like write, you have to like type your stuff in. So that's why they write it like this, because it's hard to make this little train track thing in the text box. So let me see if I can bring the text up. Okay, so they would do like um, now for the labs, when you have to show your work on the lab, you can write it like this or you can scan it in. It's totally fine. And the lab will usually tell you if it's your work shown and stuff like that. So you could write it like I did in this text box, or you could write it like this and then just scan it in. Either of those is fine. So yeah, for the labs, you can do it either way. But for a test or a quiz, most of them I think are all multiple choice, it looks like, from what I've seen, but there may be a short answer that's stuck in there somewhere, and then you would just put the text box like this. And then you could write, you know, let me see, I think my text box is too far over. Oh, now I'm making a bunch of text boxes. That's this new software for you. Okay, just deleted everything. But anyway, so you would do like that. They would do that. And then it's just, so what originally what I was going to get at is that if it's a short answer question, you really need to make sure that you write your units here. If it's a multiple choice, you know, they'll already have the units in there for you. But if it's short answer, you'll lose some points if you don't show your work, and you'll lose some points if you don't have the correct units at the end. So that just kind of keep that in mind. But that's kind of how someone would write it in the text box. They would write that question kind of like that. But if you're doing a lab or something, you're more than welcome to write it all out by hand, and then, you know, scan that in if you need to. I kind of think that's easier personally for me. Okay, I don't really want to download this. Okay, let's go back to the main screen. Okay, so then here's another one. This is a similar problem, except instead of going from something big to something small, we're going to go from something small to something big. So let me see if I can get my pen. Oh, there it works. It won't work here. Huh. Okay, I'm just gonna do by hand then. So I'll like underline this, and I'll underline this. Let me delete this scribble. Okay. So then I'll write like 390 millimeters. And I'm going to do the same thing here. Since I'm going from something really, really small to something really, really big, I'm going to go meters in the middle. And again, the reason I like to do that is because I feel like people make less mistakes that way. Because it's easier to kind of remember how many millimeters are in a meter than like how many millimeters are in a kilometer. And then I'm going to put I always like to do my units first, and then I go ahead and put my numbers in. That way I can make sure my units cross out correctly. Because if my units cross out correctly, I know that as long as I put the right numbers in the right spot, then I'll get the right answer. So I just like to make sure I have that part situated. So now I'm going to say millimeters are smaller than meters. So I'm going to say how many millimeters are in 1 meter. And that prefix milli means 1,000. So there's going to be 1,000 millimeters in 1 meter. And you see, since we're going from something small to something big, now we've got our number on the bottom instead of the top like we did before. So we're going to be dividing. And then meters are smaller than kilometers. So I'm going to say how many meters are in a kilometer. And this prefix kili or kilo also means 1,000. So we have 1 kilometer is going to have 1,000 meters in it. So then I'm going to do 390. And there's 2 ways you can do it. You can divide it by 1,000 and 1,000, or you can just divide it by like you can divide by 1,000, get your answer, and then divide by 1,000 again, or you could divide by 1 with 6 zeros, so like a million. So it's totally up to you how you want to do it. So 390 divided by 1,000. I'm going to put this in my calculator just to make sure that I don't mess it up. I like to tell my students that you don't get any bonus points for doing the math in your head. You know, you don't get extra physics superstar points. And so that's why I like to just go ahead and do it in the calculator. That way I know I'm not going to mess it up. So now I'm going to take this 0.39 and I'm going to divide that by 1,000 again. When I'm multiplying, it's easier for me to do it in my head, but believe it or not, math is actually not my favorite subject. So then I have 0.00039 kilometers. Okay, so that would be my answer. And then if it was a short answer problem like on a test or something, you could, you know, to show your work, you could do, you know, you could type in something like that, and that would, you know, that would give you your full credit. So I just, to me, it's easier for me to visualize it in the little, they call this thing a train track or a T-chart or whatever. It's just easier for me to visualize how to do it that way. But this would give you, you know, that would give you your full points if you needed to. So let's go back to the, okay. So that's kind of, we did a big to small and a small to large. So that's kind of how they work. Now, Sig Figs are kind of tricky. And they're tricky because there seem to be like a lot of rules. This says around 5 rules, but it seems to be like a lot more when you think about it. And there seem to be like all these special cases. And honestly, after we get out of this unit, we're really not going to mess with Sig Figs really anymore. So if you turn like in a lab with an answer and it's not in Sig Figs, as long as you have the right answer, I'm giving you credit. I'm not gonna be like, oh, it's the right answer, but it's not in Sig Figs. I give you credit after, you know, after the first unit, but we have to learn Sig Figs. It was the same way in my face-to-face class. We had to learn Sig Figs, and it's just, you know, but we didn't really use it much afterwards, so it's kind of silly. So the important part with Sig Figs is zeros. And then there's different rules for addition, different rules for subtraction. So we'll go through both of those. So a zero that's like in front of a decimal point, and there's nothing in front of that zero. It just kind of makes the decimal point stand out a little better. That zero is not significant. It doesn't matter. If you have these zeros here, these are placeholder zeros. They are not important either. So they're not significant. But these zeros in the middle are. So if you have zeros in the middle, of two like regular numbers, they're considered significant. And then if you have zeros at the end, they're significant as well, because basically these are just here. They're like a means to an end, right? You just put them there so you can get to the actual like good part of the number. And these at the end, someone took the effort to write those zeros at the end, so that means they're important. They're showing you that that place has actually zero and that place is actually zero. And then regular numbers, numbers that aren't zero, are always significant. So what I did on the next slide is I put a bunch of numbers in here, and then I thought that we could go over and we could try and figure out how many sig figs are in each of these numbers. So there used to be some quiz questions. I took them out. If you have a number like this, where it's like 1,000 or 1,500 like this one, but it doesn't have a decimal at the end, this is where it gets tricky, because these zeros, you don't know if they're significant or not. If you had the zero here, then it would definitely be significant, but they didn't do that. It's just 1,000. And so we know that the 1 is definitely significant, so I'll put a Y here. But we don't know about these 3. Because there's no decimal, we're not sure. So they call these numbers ambiguous. And so there were some quiz questions that had these ambiguous numbers on them, and I deleted them all, so you won't see any ambiguous numbers on the test. But just, for your information or whatever, if you have a number like this, if they had like a 0 at the end of this 742, so 7420, this one would be ambiguous too, because we don't know if that 0 is significant or not. If they had a decimal place, it would definitely be significant, but since, if they don't have a decimal place, you don't know if it's significant or not, that last 0, those trailing zeros. So that's kind of where it gets tricky, because it's kind of hard to figure out how many sig figs you have, which is, then when you get to like math and subtraction and or addition, subtraction, multiplication, division, and it depends on how many sig figs you have in your number, for how many sig figs you have in your answer. If you get something like 1,000 with no decimal point, that's really confusing. So I took all those out of your test. So this one basically could have between 1 and 4, and we're just not really sure which. Now, if we went to this 1,500, this is definitely significant. This is definitely significant. Since we have a decimal here, these two are also significant. Okay, those two zeros. So then we would have, this number would have 4 sig figs. And I'm just going to write SF rather than writing sig fig. I'll write that here too. Does that make sense how the 1,000 with no decimal point and the 1,500, how we know exactly how many sig figs we have with the 1,500, but not with the 1,000? Okay. Just if you have a decimal place, it's definitely, these zeros are definitely significant. If there's no decimal place, so if it was like, let's see, if we had 1,500 like this, we would know this was significant. We would know that was significant. These we wouldn't be sure of because there's no decimal place. So we would say that this one has between 2 and 4, but we're not certain. So they call those numbers ambiguous. And it all has to do with the decimal place. So if you get a number like 1,500 on your test or your quiz, there'll definitely be a decimal place. There's no numbers like 1,000 or 1,500 or anything like that without decimal places, because they are ambiguous and it's hard to tell. Now let's go to this little one. This is a tiny number. This one is definitely not significant, and this one I know. I know. Every year, I'm not even kidding. I have to go and I have to go watch the videos of myself explaining Sig Figs, um, because I forget. Because I do them in this one unit and then I never, deal with them again. So, yeah, I have to actually watch myself teach. I have to teach myself, like watch videos of myself teaching, um, in order to figure it out. Um, so it's not just you. Um, so these front two are considered not significant because they're just in the front and they're just like a means to get to the good part of the number. Um, they're like a means to an end. This one is significant, this one is significant, and this one is significant because it's a regular number. It's not a zero. And then because this zero, someone took the effort to put this zero at the end, this zero is also significant. So this number would have 4 sig figs. Oh, I just said that I didn't want to waste time writing sig fig, and then I started. Um, so this one has 4 sig figs because this one counts, this one counts, this one counts, and that last zero counts. The front two zeros don't count. They're just a means to an end, a way to get to the rest of the number. If we go to this 10, this 1 is significant, this 8 is significant, this 5 is significant because they're actual real numbers. And then because these zeros are in the middle, sometimes I call them sandwich zeros because they're sandwiched in between normal numbers. They are considered significant. Those two zeros are considered significant. So this one would have 5. This one would have 5 sig figs. So these middle zeros count. If we go to this bottom one, since this bottom one all has regular numbers, there's no zeros in it at all. Um, this one's kind of easy. I like it when I see numbers like this because then I don't have to worry about if the zero is significant or not. So this one would have 3 sig figs. Um, and then if you see over here, I put that same number, but then I did dot zero. This dot zero is saying that we have 742 exactly. So somebody took the effort to write that decimal and then write that zero behind the decimal. And so that means that that zero is significant as well. So this one would have 4 sig figs. Okay. And then we'll do this last decimal one. This is a decimal at the very front, in front of the decimal, or it's a zero in front, so it doesn't count. This zero doesn't count either, and this zero doesn't count. So these 3 zeros don't count. They're just a means to get to the good part of the number, so we don't count those. This one counts, this one counts, and this one counts. And then this zero here is a sandwich zero. So it's in between these two numbers. It's just like the zeros in that 10.085. So it does count. And then this zero at the end, someone again took the effort to write that zero at the end. They're saying that it's exactly that number. And so that zero counts. So this one would have 1, 2, 3, 5. This one would have 5 sig figs. Does that kind of make sense how we determine the sig figs in an individual number? Because then we're going to go, when we do the math, we're going to go like, okay, great. We're going to go one step further and we're going to figure out the sig figs in math. Okay, so this is the rule for multiplying and dividing. It depends on the total number of sig figs. So your answer can't have more sig figs than, I'm a science person, I could not remember the math word for the things that you're multiplying in a multiplication, so I called it the reactant. That's like a chemistry term, like the things that are being multiplied with the least amount of sig figs. So your answer can't have more sig figs than the thing that is the smallest or has the least number of sig figs in your that you're multiplying. So let's just try it. Um, so we have this one. So the first thing I like to do is I like to write the number of sig figs like above the number. That way I kind of know, and then I'll get the answer, and then I'll make that answer whatever it needs to be in sig figs. So this 4 is significant, the 2 is significant, the 6 is significant, and since somebody took the effort to write decimal 0 or dot 0, that 0 is significant. So this one's going to have 4 sig figs, and then this 2 is just the 1 sig fig. It only has 1. Okay, so I'm going to do the same thing. I'm going to put it in my calculator. I see students all the time. They do like sig fig problems and they have like easy numbers, and so they just try and do it in their head, and then they get the answer wrong because they got the answer wrong. Like they multiplied it wrong instead of like how many sig figs it had. So this one is 852. So we can only have one sig fig. So what we're going to do is I'm going to round this up to 900, and I'm going to have that be my answer. Now, if I wanted to be really good and I wanted to be really specific, since 900 is kind of ambiguous, I could do 9 times 10 to the 2, because we have 1, 2, and this is the problem with this unit. They discuss sig figs before they discuss scientific notation. And so they don't give you a way to kind of get out of those ambiguous numbers. But that's how I would do it. And then we'll discuss scientific notation in a little bit. But anyway, that's how I would get rid of that ambiguous number if you need to. But if you just put 900, you would be okay. If it was like a short answer question. If it's a test question, a multiple choice, then they're going to give you, probably 900 as a choice. You couldn't just put 900 dot, right? Because then you'd have 3 sig figs. So that's probably the best way to write it, 9 times 10 to the 2, but 900 is okay. Now let's try this one. We're dividing. We've got a little number and then a normal number. So this 0 does not count because it's in the front. This 0 does not count because it's also in the front, right? It's just a means to an end. But this 2 does count because it's a normal number. So we have 1 sig fig, and then this is a sig fig, and this is a sig fig because it's just a normal number. So we have 2 here. So again, our answer can only have 1 sig fig. So I'm going to put this in my calculator just because I don't want to get it wrong, for that. And then, so luckily, my calculator gave me that. So that's 1 sig fig right there. If, let's say I needed 2 sig figs, right? Let's say this one had 2 and this one had 2. So I had to have 2 sig figs. I could just add an extra 0 on the end here, and that would give me my 2 sig figs because the 8 would be significant, and I took the effort to write that extra 0, so that 0 would be significant. So since they only wanted 1, I can leave it this way, but if they wanted 2, I could write another 0. If they wanted 3, I could write 2 zeros, whatever I needed to do. I could just add some more zeros at the end if I needed more sig figs. Now, let's try this bottom one. This 1 is significant, this 5 is significant because they're just normal numbers. This 0 has a decimal after it. So that means that 0 is significant. So we're going to have 3 here. This one is not significant because it's a 0 in the front. This one's not significant because it's a 0 in the front. This 2 is significant because it's normal. It's a normal number. And this 0, someone took the effort to write the 0. So that means that one's significant. So this means our answer is going to need to have 2 sig figs. Okay, so now my answer is 3. This is what the calculator gave me, right? But I need 2 sig figs, right? I can't just put a 0, right? Because then that's 30. So what I have to do is I have to draw a decimal, and then put a 0. And since I took the effort to draw that decimal and the extra 0, 3.0 would give me 2 sig figs. And so I'd have my 2 sig figs for my answer. So I would be okay. Does that kind of make sense how those work? Okay, excellent. Okay, now let's go to addition and subtraction. So addition and subtraction depends on the total number of decimal places. Your answer can't be more precise than your least precise, again, the thing that's being added or subtracted, okay? So we don't care about total sig figs. You can have as many as you want. All we care about is decimal places. That's really what we're going to focus on with these. So this one, this 426 has 1 decimal place. And this 2 has 0 decimal place. I'm going to draw the 0 like that so you can tell it's a 0, not an O. Okay, so when I add these together, I need to have an answer that has 0 decimal places. It can't be more precise than this 2. So we could do 4. I'm going to try and do this one in my head because I think I could do 6 plus 8. We'll have 428, and technically it would be like 428.0. But that gives us a decimal place. So then our answer would just be 428. And that gives us our 0 decimal places. So now let's check this next one. This 25.0 has 1 decimal place, and this 0.02 has 2 decimal places. And since it can't be more precise than the least precise thing that we're subtracting, our answer can only have 1 decimal place. So it can't be, we can't go to that 0.2. So let me get I'm going to do my calculator just to be safe. So I'm going to get 24.98. Now, this one's kind of silly. Since we can only have 1 decimal place, right, we've got to get rid of this 8. Well, since it's 8, we have to round up. Well, since that 9 is already a 9, we end up actually with 25.0 again. So it looks like we didn't even do anything. Because this one is just so tiny, it's not really affecting that at all. So that's kind of how that one would work. And that's just because this is that 9, 8, so that 8 rounds up, and then that 9, has to round up. Then you've got to keep the decimal place. So that's how that one works. Now let's try this one. We have 150.0, so we have 1 decimal place here, and then we have 15.52. So we have 2 decimal places here. So our answer can only have 1 decimal place. So I'm going to do 150 minus 15.52, and I get 134.48. Okay, and again, we can only have 1 decimal place. We have an 8 here, so we've got to get rid of that 8, but we have to round up. So then we end up with 134.5. Does that make sense? The biggest thing that I noticed with students that are doing addition and subtraction or multiplying and dividing is they'll mess up the rules. So like for addition and subtraction, instead of caring about decimal places, they'll look at the total number of sig figs, or like for multiplying and dividing, they'll look at the total number of decimal places. And so that's really where we have the biggest problem, usually what I see, is students mix up the rules between addition and subtraction and multiplication and division. So now, this is scientific notation. I'm sure you've probably done this before in your other classes. If you've taken chemistry, you kind of have to do it in order to write some of those big or small numbers in chemistry. But basically, it's a way that we can write very large or very small numbers. And then when you're doing sig figs, it's also nice because you can show a really particular number of sig figs. Um, and so for this one, what we do is if we have a big number, we're going to write times 10 to the, and this number up here is going to be positive. If we have a small number, we're going to write times 10, and this number is going to be a negative. And that tells you that this you have a really small number. And so what I do is I just start here and I go 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, we're going to work on graphing. Don't worry. I'll do this really, really quick. So for this one, I would do 4.23. And you always, when you do scientific notation, you always want to have one number in front of the decimal. So you wouldn't want to do like 42.3. You would always want to do like 4.23. So how many was that? 3, 6, 9. Okay, 9. Okay, now this one, I'm going to do this really small one. 2, 3, 4, 5, 6, 7. I'm only going to count to that first one because, I only need to because I only need to have one in front of it. And then for these, I mostly put these here because I wanted to show you guys how you can do this in your calculator. And so there is a button in your calculator that is like a big E, and you can write like 5.5 e to the 5 plus 7.2 e to the 2. And then you don't have to worry about like writing times 10 caret whatever. Because sometimes when students do that, they don't put enough parentheses in place, and then um, the the answer turns out incorrect. And so for this one, I got this. So that's how you would write that one. And then if you wanted to, you could do like 5.5 times 10 to the 6, or times 10 to the 5. But it wouldn't look like you added anything. So anyway, I just wanted to show that you can use that big E there because it just saves a lot of effort when you're doing math. Okay, so now we're going to get to graphing. Okay, so in science, all your graphs need to have a title. They need to have the x-axis labeled with the unit. So let's say time. We have time a lot on the x-axis. You would need to write like you would need to write time in seconds. That way I know you're doing in seconds instead of minutes or whatever. Your y label, your y-axis needs to be labeled with units, same kind of thing. If it's force or you would do newtons or whatever meters. Your x and y axis needs to be labeled evenly. So you need to do like 2, 4, 6, 8, 10. You can't do like 2, 3, 7, 9, 10, 12. It needs to be even because the point of a graph is to kind of show you some patterns in science. And if you don't have, if your graph isn't labeled evenly, you're not going to get those patterns. Another thing, sometimes in math, they show you that you can do these like squigglies. Like you can write some numbers and then do a squiggly. Don't do the squigglies in science. You could just call it a trial. Like for your graphing lab, you could just call it trials. Trials don't really have a unit, so you wouldn't have to worry about that. So don't do those squigglies in science. Otherwise, it's going to mess up your pattern. You're not going to get to see, your curve or whatever you've got. It'll just mess it up. Your points need to be plotted correctly, and then you want to have a best fit line, not a connect the dot line. And we'll talk about best fit lines in a second, but basically a best fit line is the line that's going to be as close as possible to all your data points. So like some teachers teach, I met a guy, he was a retired science teacher, and he taught my students when I was out on maternity leave to connect the first and the last point. A lot of people do that because they think it's really easy, but that's not a best fit line. It's entirely possible that your best fit line may not touch any of your dots at all, and that's totally okay. You want it to be as close as possible to all of your dots. When I think about a best fit line, I think about like, I think that let's pretend all my dots have feelings, and I don't want any of my dots to get like left out. And so I want my line to be as close as possible to all of my dots. Um, and so that's how I draw a best fit line. It's kind of silly to think about my dots having feelings, but that's kind of how I do it. So this is kind of a visual of what I was talking about. You see how they've got their time, their independent variable in units. So like your lab, you're doing like a trial and then like number of heads or something like that. And so your trial is going to be your independent variable, and then the number of heads is going to be on your y-axis. That's going to be your dependent, because the number of heads depends on how many trials you had. And so that's kind of how I think about it. What, like your temperature is going to depend on your time or whatever. And just as like a aside, if you have time as one of your things that you're trying to graph, time is always on the x-axis, always, always, always. So I like graphs with time because then I don't have to figure out who's independent and who's dependent. I know that time is independent and I'm good. And so you see here, you see how they labeled them both with 0. So they have 0 at this intersection here, right here. And then in this one, they went 5, 10, 15, 20, 25. That's what I meant by labeling the graph evenly. And you can see on the y-axis, they used a totally different numbering scale. So even though they went by 5s on the x-axis, that didn't mean they had to go by 5s on the y-axis. So they went 4, 8, 12, 16, 20. So in here, it looks like they've got connect the dot lines. Let me see if I could. So for like this one, you know, if I was going to try and draw a best fit line, this is not a very good one because I can't draw straight with this pen. I would try and do something like this because it looks like then, you know, there's no point that's like, you know, way out here, really, really far away from my line. It seems like they're all pretty even to my line. So that's kind of what I would do for that. For your pennies lab, you're going to have one that is a straight line, and then you're going to have one that is a curve. Get the drawing tool back. You'll have one that's a curve kind of like that. So you will have one straight and one curvy one. So just, you know, that's okay. So let's talk about the types of graphs. So a bar graph is used when our data is not continuous. So like January, February, March, April, May, June, those are discrete quantities. Apple, orange, banana, you can't have like, you know, you couldn't have a point right here, right? It wouldn't really make a lot of sense. What is that? Half apple, half orange, right? That kind of doesn't make a lot of sense. If you were doing like, excuse me, like colors of M&Ms, that would be one that you would want a bar graph. Technically, I've seen, because you can have, you know, a point here, what is that, like partway through January, February, like when I see temperature data, a lot of times, you know, it'll be a line graph kind of like this for the different months, because you can have, you know, like partway through April or, you know, that kind of thing. But overall, it's usually when you've got things that don't make sense as like a halfway, like, you know, can you have a blue-green M&M? You know, it doesn't really make a lot of sense. And then a line graph is used for continuous data. So when in doubt in our class, make a line graph because physics data is almost always line graph data. Um, and so they're going to look like this. You're going to have a bunch of dots, and then you're going to kind of make a line that connects your dots. Now, do you see this best fit line right here? Do you see how this point over here is like much farther than all the other points? Um, I wouldn't call that an excellent line graph. If I was going to draw this graph, I would draw it. I'm not even going to try and draw a straight line, but I would draw it a little closer to that guy. You don't want to be too far away from this one, but I would draw it closer to this. Now, since I wasn't, I didn't collect this data, it's entirely possible that this is what they call an outlier. And something weird happened when they were collecting this data. And so this point, they told the software to ignore that point because it was, something weird happened when they collected that data. Like they tipped over their sample bottle or, something weird happened. So it's entirely possible that, they had told their program to not worry about that one and just think about all the others, in which case, then I'd still want it to be a little closer to this guy. But I would, if it wasn't an outlier and I wasn't trying to, I didn't have like a specific reason to get rid of this guy, I would probably make my line a little closer to him. But that's just me. On this one, you can see they did a pretty decent job, given that it's a curved line. This one's a little farther out, but it's still pretty close. I would kind of go with that. This out here and this out here, these must definitely be outliers that they've told the software not to look at because they're a different color and something must be wrong with these. So these best fit lines, like this one, there's only actually one data point that touches this best fit line, and that's totally okay. You could have 0 points touching your best fit line. It doesn't really matter. The reason this one is touching the first one is just because that one also happens to be on like that y-axis like that. But it usually, like if you have a straight line like this, you see the best fit line isn't actually touching that first. So usually when I grade these, the first thing I do is I look to see if you connect the first and last dot. And if you did that, I look and see if that made sense because it usually doesn't. And so that's how I can tell usually if you know how to make a best fit line or not. Because if you connect the first and the last point and it doesn't make sense to do that, then I know that you really don't know how to make a best fit line. And then I know that's not really what you did. You just connected the 2 points. So line graphs are going to be used for our kind of data that we use in this class. And you can see like this one. Do you see how they have number for their y-axis, but their number doesn't have a unit? That's just because like number of ants doesn't have a unit. And so that's okay. But if it is something that should have a unit, like seconds or velocity or something like that, then you're going to want to put the unit. So I know that you're doing it in seconds instead of minutes or seconds instead of hours or whatever, because your data will look different. This one is just an interval, and so it doesn't have there's no units here because it would make sense to put units there. So that's kind of how we do graphing. Do you have like specific graphing questions, or did I answer them, or? Oh, how do you resubmit your graph? Okay. Just go back into the Dropbox and add your new file, and it will show me that that you have a new submission, and I'll go check it. And then if you miss one of these talks, on the right side of your course, you kind of have to scroll down a little bit. It says user links, and there'll be a link to all of these Jigsaw sessions. So like there's one from last week, but it's just like a welcome chat. But they'll all be there. So yeah, if you ever miss one of these, you can always find it there. Hopefully that's what everyone else is going to do. Um, but you never know. So, I did put a couple of attachments here on the bottom. These are extra practice problems I used to do with my face-to-face kids. Um, you don't have to download them. Don't feel like obliged to download them, but if you feel like you want extra conversion practice or Sig Fig practice or whatever, um, I put those there just so you'd have some extra practice problems. Um, but otherwise, um, that's kind of all I had for you tonight. Hopefully that helped you review for your test.